In this video, we're going to start talking about the graphs of functions in a higher number of dimensions. But let's briefly begin by studying what we did in first year calculus. This is when you'd have a graph that looked like this, so y equal to x squared. And what was important back in the day was that you had a single input x and you had a single output y. Maybe the x and y would be called different things, but it was a function from one dimensions to one dimension, and the graph, which was two-dimensional, was able to capture sort of the input values and the output values at the same time. The way this worked is, let's imagine you didn't know what y equal to x squared looked like. One of the ways that you could start to plot this would be, well, you might look at the x values first, and I could put a few down here, special ones, 0, 1, -1, 2, and so forth. Then you could go compute. 0 squared is 0, 1 squared is 1, 2 squared is 4, and you could then plot all of the heights above those input points that you specified. Indeed, when I go on the computer and tell it to plot this, this is what it's doing. It's breaking the x-axis into a very large number of points. It's figuring out the height above a very large number of points. It's just plotting all of those points, and we just can't see the divisions between them. So let's take that same idea and go up a dimension. And what I'm going to do now is I'm going to consider functions of x and y with an output of z. That is, there are two different inputs, the x and the y, that get fed into my function, and I still only have one output z. In this case, I'm considering the function z equal to x squared plus y squared. And it's going to look a little bit like this, and we're going to figure out how to think about this, how to come up with this shape a bit later on in the video. Now, we live in three-dimensional space, so it's easy to visualize stuff in 3 dimensions like this particular surface here. And it's easy to represent mathematical objects in 3 dimensions. It's quite reasonable to have functions that depend on more than just x and y. For example, maybe your functions depend on x and y and z and t and who knows, any number of other things. It's also fine to have outputs that are higher dimensional as well. You could have an x and a y and a z that all change based on different types of inputs. Now, there's one nice thing about having 2 inputs and 1 output, is that the sum of 2 and 1 is 3, and this 3-dimensional graph, well, we live in 3 dimensions. We can visualize things in 3 dimensions. It's possible to have more inputs, and it's also possible to have more outputs. That's all entirely okay. It's just you can't graph it quite as nicely in 3 dimensions. Now, let's imagine you have no idea how to graph x squared plus y squared equal to z. How could you begin? Well, let's do exactly what we would have done in the case of a 2-dimensional graph. Now my inputs is this entire input plane. And I'm going to put a grid of values here, like 0, 0, 0, 1, 1, 0, and so on. These are a bunch of allowable inputs down on my input xy plane. I could then go into my function and figure out, well, what's the height? What's the height above the point 0, 1? Well, it's 0 squared plus 1 squared, which is 1. What's the height above, say, 2, 3? Well, it's 4 squared plus 3 squared, which is 13. So above all of these blue input points, you can get these red heights, and then if you put all the red heights together and plot it with a sufficient resolution, computing enough points, you could get the visual that this is representing this sort of bowl-shaped object. Now, that's not bad. However, it's quickly going to get tedious computing the values of a whole bunch of points. So I want to get a little bit better where I can visualize what's going on without computing an enormous number of points. One of the things that I did to help the visualization here is you see there's all these circles that are going around. I drew these circles as part of the way to visualize that it was a bowl. What these circles represent are something called contours. What a contour is a fixed height of the function. It's the f of xy, all of the xy points, where it's equal to some fixed output value like 1 or 2 or 3. That's what these circles represent on this particular x squared plus y squared equal to z. So now what I want you to imagine you're going very high above this picture and you're looking straight down at it. So you've got sort of a bird's eye view looking straight down from very, very high up on the z-axis. So now I want to visualize what would just the contours look like. I'm going to just take those contours and look up very high, and I'm going to project them down onto the xy plane. So what you get is all of these concentric circles down in the xy plane for this specific example. The reason they're all circles is because my function is x squared plus y squared equals a number. And x squared plus y squared equal to r squared gives the circle of radius r. So this gives me a new method to come up with how to visualize this. I can say, what are the contours? Now in this example, there's a couple different possibilities. First of all, c can never be negative because x squared plus y squared is certainly positive, can never be negative. So the smallest c that even has a contour is the case when it's x equal to 0, y equal to 0, and c equal to 0, so just a point. And then as you increase the value of c, make it more positive, you get circles with wider and wider radius. And indeed, that's exactly what it visualizes as. All right, I'm going to go in reverse. I'm now going to give you the contour plot for some function. Indeed, I've color-coded it so that the yellows are meant to be higher values and the blue values are meant to be lower values. But nevertheless, any curve in the xy plane that I have here in my contour plot, so the contour plot is just looking at the inputs, just looking at the x and y's, and it's saying that these curves represent all being at the same height, with yellow being higher values and blue being lower values. That's how I'm color-coding it. Okay. I want you to pause the video and try to answer the question, what does this actually look like as a surface in 3 dimensions? That's all right. I'll just wait. You pause, go and try to visualize it. Okay, thank you for the pausing and trying to think about it. The result I have gotten is this graph. It looks a little bit like a Pringles chip. Indeed, what we've had is that in the yellow portions, it's relatively high, in the blue portions, it's relatively low, and that sort of midpoint occurs directly in the center. And the reason that this represents the function, I've now input the function, x squared minus y squared, is imagine first that y was equal to 0. If y was equal to 0, then you'd get z is equal to x squared. It would be a parabola that looks like it's going up. And this indeed looks the case. It looks like you're at a mountain pass, and on one direction is a parabola going up and getting increasingly yellow. But then if I imagine that x was 0, you'd get z is minus y squared. Well, z equal to minus y squared is also a parabola, a down-facing parabola. So you sort of imagine that you're a mountain pass. There's one direction where you can go up to 2 peaks on both sides, and another direction where you go down into the blue into 2 valleys on both sides. And so a contour plot is a very useful way to help us visualize the graph of a function before we've actually seen its graph. We can go and compute out what the contours are going to be, and then we can use the contours to go and visualize this.